Today we're going to start chapter 12. We are going to look at chemical kinetics in chapter 12. And chemical kinetics is the study that looks at the rate of a reaction. So in first year chem, I know that we would have been remote possibly. We would have looked at the factors that affect the rate of a reaction. Okay. And you would have also looked at this the other day when you looked at our Clorox reaction with our water with food coloring. Okay. And so some things you may have listed in your assignment are we can change concentration, and that will affect the rate of a reaction. We can change the temperature, and that could possibly affect the rate of a reaction. We can change the surface area, and that will affect the rate. And then other things that we could use is if we add a catalyst, that will affect the rate of a reaction, or adding an inhibitor will affect the rate of a reaction. All right, so let's look at the content that's in section 1. We're going to talk about reaction rates. And what we're looking at here is the time for change. So there are some things that maybe we can visually see that tells us that a change has occurred. So you may remember from first year chem, color changes. So you could time how long it takes for a color to appear or maybe a color to disappear, which would be our food coloring with our bleach. You can measure energy changes. So if it heats up, if it cools down, so endo and exothermic. You could measure gas pressure, so the time it takes for bubbles to appear or for fizzing to occur. And then also, we know that another type of evidence of a chemical change is the formation of precipitate. So, time how long it takes for that precipitate to appear. So, this is the reaction we're going to talk about in terms of rates of reaction. So, I have nitrogen monoxide. Actually, this should be nitrogen dioxide. And it's going to decompose into nitrogen monoxide and oxygen gas. All right, so this reaction occurs, data was collected, and this graph was constructed. All right. So remember that we talked about rate. It was talked about being a change over time. So in this case, what we're going to talk about in terms of rate is we're going to look at the change in concentration over time. And notice that I wasn't specific about our time unit. So sometimes it will be in minutes, sometimes it could possibly be in seconds. And so the way we would represent this in an equation, there would be a delta symbol. That delta refers to the change. And then there are brackets. The brackets represent whatever number we see inside these brackets is representing the molarity. And we know molarity is moles per liter. And for now, we're just going to be generic. We're just going to say that our substance is A. And this is per unit time. So again, the change in time. and time can be seconds or minutes. And it's important to note that when we talk about reaction rates are always positive. Okay, so let's look at reaction rates in terms of my equation here with nitrogen dioxide decomposing. So it would be the change in concentration of NO2 over the change in time. Now, this is my reactants, so we should know that reactants are used up during a chemical reaction. So the concentration of NO2 is actually going to decrease. And remember, my rate always has to be positive. So if we're writing the reaction rate for a reactant, we're always going to put a negative sign in front so that the rate will be positive. All right. And then if I look, the coefficients in my equation for NO2 and NO are the same. And if I look at the curves for these two, for NO2 and for NO, okay, the curves are also the same, but they're inverted. And that's because one of them is the product and one of them is the reactant, and they have the same coefficient. So the reaction rate for NO2 and for NO are going to be the same. All right, and then there was one more species in our equation. So the other species in our equation is oxygen. And if I look, oxygen's curve on our graph here is not the same. And if I look, the coefficient would be different. So here, if we're talking about the rate of O2, I could take the rate of NO and we could multiply it by a mole ratio, where we're going to go from moles of NO to moles of O2. And my mole ratio uses the coefficients in my balanced equation. So based upon coefficients, we can see that the rate of NO is being produced is twice the rate of O2 being produced. All right, and then one last vocab term for this section is instantaneous rate. And here we're looking at the rate at a particular time. So if I look at my graph here, you can see that they're computing the slope of a line tangent to the curve at a point. Okay. This work would represent the instantaneous rate.